Three things that don't look related. A page that freezes solid the moment you click a button. Nothing responds for 2 full seconds. A loading spinner that keeps turning perfectly smoothly on that same frozen page, as if nothing were wrong. And a timer set to 0 milliseconds that somehow runs last. They look like three unrelated problems. But the same hidden mechanism explains all three. And four more you have probably run into without ever getting a straight answer. So let's make that mechanism visible. Here's the dashboard. This button builds a report out of 40,000 rows of data. Watch what happens when I click it. And don't watch the button. Watch everything else. Cancel doesn't respond. I can't select this text. And look at the chart. It's supposed to redraw with the new numbers, and it hasn't moved at all. For 2 full seconds, this page is a photograph. Everything is still on screen. None of it works. Now, the usual explanation is that JavaScript is single-threaded. That's true, but on its own, it doesn't tell you why the chart stopped or why cancel stopped. So let's actually look at what the browser is doing. I'm going to draw time as a line, running left to right. This is the same basic idea as the performance panel in your developer tools, so it's worth getting comfortable with. Every time your JavaScript runs, it takes up a piece of that line. Here's a small one. That's the browser handling a click. Now, here's the part that matters. And it's the part most explanations skip. Updating the page, working out the new layout and putting fresh pixels on your screen is something the main thread does in between those pieces, not during them. In between. I'll mark each of those moments underneath the line. When the pieces of JavaScript are small, there's room between them, the browser gets its chance, and the page keeps up with you. That's what a page that feels alive actually looks like. Now let's click our report button. One click, one piece of JavaScript, and it runs for 2 seconds without ever stopping. There's no room after it because it hasn't finished. And there's no room inside it because JavaScript doesn't get interrupted halfway through. So there's nowhere for that update to happen. That's your freeze. It isn't the browser being slow. The browser never got a chance to move on. And that gives us the sentence this whole video rests on. For the main thread to update your page, your JavaScript has to leave a gap. Except, look at the spinner. The page is frozen. Nothing responds. And that spinner is going round perfectly smoothly, at full speed, the entire time. If everything is stuck behind one long piece of JavaScript, how is that still moving? Because it isn't on this line at all. When you animate certain CSS properties, transform and opacity are the two big ones. The browser can often hand that animation over to a completely separate thread called the compositor. And if the browser can composite that animation, it may have everything it needs to keep producing frames even while the main thread is blocked. So it gets its own line. And when the main line jams solid, this one just carries on. Which is genuinely worth knowing because it changes what a spinner tells you. A spinner means your code thinks it's busy. It does not mean your page can still respond. So next time you're staring at one, wondering whether the app has died, don't trust the spinner. Try to select some text. If you can't, the main thread is blocked. So the piece of JavaScript is too long. The obvious fix is to make it asynchronous. So the developer marks the function async, drops an await inside the loop, and the reasoning goes, await means wait. Waiting means pausing. Pausing means the browser gets a chance to breathe, ship it. And the page freezes for exactly as long as it did before. Not slightly better, identical. This is the most useful thing in this video, so I want to take it slowly. Here's what actually happens when you hit that await. Your function does stop. Control genuinely does go back to the browser. That part of the reasoning was right. But the browser doesn't get a gap out of it. And here's why. When your function pauses, something has to remember to start it again. That instruction goes onto a list. Not the ordinary list of jobs the browser works through, a second list with higher priority. And the browser's rule for that second list is strict. Before it moves on to another task or gives the page a chance to update, it empties that list. That list has a name, by the way. It's the microtask queue, and the jobs on it are microtasks. Now, what did you await? Promise.resolve. A promise that had already finished before you even awaited it. So there is nothing to wait for, and the instruction to restart your function goes onto that list immediately. So the browser looks at the list, and there's a job on it. It runs that job, which is your loop carrying on. And your loop immediately schedules the next one. It isn't a pile getting bigger. In this loop, every time the browser checks, there's another continuation waiting. It runs that continuation, which immediately schedules the next one. The list just never reaches empty. And until it's empty, the browser is not allowed to move on and update anything. So look at what that does to our timeline. Your work is technically in pieces now, but the pieces are touching. There are no gaps between them. And a page with no gaps is a frozen page, no matter how many awaits you put in it. You didn't need to pause, you needed to let go. That second list also explains a puzzle you have almost certainly been asked in an interview. 4 lines. Log start. Set a timeout for 0 milliseconds that logs timeout. Take a promise that's already resolved and log promise from it. Log end. 0 milliseconds. So the timeout should come second, shouldn't it? Have a think about what you'd expect. The real order is start, end, promise, timeout. And now you can work out why, instead of memorizing it. Start and end are ordinary lines of code. They're part of the piece of JavaScript that is running right now. So they happen first in the order they're written. The promise callback goes onto that second high priority list. And we already know what the browser does with that list. It empties it first, so it runs next. And setTimeout doesn't touch that list at all. It asks for a brand new job on the ordinary queue. The browser only starts a new ordinary job once it has finished everything else, including its chance to update the page. So it goes last. The promise isn't faster than the timer. It's just sitting on a list the browser is obliged to finish first. And that 0 was never a promise of speed. A delay tells the browser the earliest moment it may run your code, not when it will. Put that tab in the background and the browser will happily hold it far longer than you asked. Now back to our frozen page because there's something we still haven't explained. While it was stuck, I clicked cancel 4 times and nothing happened. Then the report finished and all 4 fired in rapid succession. They weren't ignored. In this demo, every one of those clicks was recorded and queued. Because running a click handler is a job, and jobs wait behind the enormous one that's already running. So they sat there and waited their turn. And the page couldn't even show you that it had heard them, because showing you a pressed button means updating the screen. And that was stuck behind exactly the same job. That's the real cost of a frozen page. Your user gets nothing back, assumes the click missed, and clicks again. And now you have 4 reports queued instead of 1. So how do we actually fix this? We know what we need now. Not pausing. Gaps. So instead of doing 40,000 rows in one go, we do a few hundred, deliberately hand control back to the browser, and then carry on where we left off. And here's why that works, when awaiting a resolved promise didn't. The timer itself becomes a new ordinary job, and the browser has to finish everything it's currently doing before that job can even begin, which includes its chance to update the page. Then, when the timer job runs, it resolves the promise, and your function picks up right after it. That's the gap. The one the resolved promise never created. Look at the timeline now. Real space between the blocks. And in those spaces, the browser can finally do its work. The page stays alive while the job is still running. There's also a purpose-built version of this called scheduler.yield. It gives control back and then schedules your work to continue through a prioritized task. instead of relying on a timer to wake it up. That usually lets your work resume more predictably. Now, the honest part, because chunking is not free. First, the whole job now takes longer. Every gap costs you something, and you're adding hundreds of them. You are deliberately trading total speed for responsiveness. And second, which means chunk size is a real decision. Too big, and you're back to freezing. Too small, and you'll spend more time stopping and starting than actually working. One practical note: scheduler.yield still isn't available everywhere, so feature check it and keep the timer version as your fallback. There's one more option, and I want to be clear about what it is, because it often gets confused with the last one. Chunking and yielding keep the work on the main thread. We're just putting it down regularly so the browser can get a word in. A web worker is a different thing entirely. It moves the heavy computation onto a genuinely separate thread, its own line, so that work no longer occupies the main thread at all, which sounds strictly better, and sometimes it is. But a worker can't directly read or update the page. No DOM, no interface. Everything has to be passed back and forth between the two threads. And what you pass and what that passing costs becomes your new problem. Different tool, different trade off. And that one deserves its own video. So, 7 things that look completely unrelated. The page froze because one piece of JavaScript ran for 2 seconds with no gap anywhere in it. The spinner kept moving because the browser could run that animation on the compositor away from the blocked main thread. Async changed nothing because awaiting something that had already finished doesn't create a gap. Your coder just carries straight on in the same block. The promise beat the timer because it was sitting on the list the browser has to empty first. 0 didn't mean 0 because a delay is the earliest time your code may run, not the time it will. The clicks stacked up because running a click handler is just another job waiting its turn. And chunking worked because it created real gaps, and the browser used them. Now that you can see all of it, here's the proper name for what you've been watching. The piece of JavaScript is called a task. The high priority list is the microtask queue. And the browser's chance to update the page is a rendering opportunity. Task, microtasks, then maybe render. Round and round. That is the event loop. You've just watched it 7 times. So, one idea underneath all 7. For the main thread to respond, to redraw, or to run anything else, your JavaScript has to let go, which gives you the question to carry around. When you're looking at some async code and wondering whether it will keep your page alive, the question isn't, is this asynchronous? Asynchronous on its own doesn't tell you anything. The question is, does this actually let the main thread go? If you await a promise that has already settled, your function is ready to continue almost immediately. And callbacks you schedule with .then or with qmicrotask go on to that same high priority list. None of those gives the browser a useful gap on its own. But when you're genuinely waiting for something that hasn't happened yet, a network response, a timer, a scheduler yield, the browser can finish what it's doing and take its turn before your code becomes ready again. So, don't ask whether the code is async. Ask whether it actually lets the main thread go. If you like seeing what the browser is really doing underneath your code, subscribe. That's what we do here. And that worker door we didn't open, moving work of the main thread solves this problem and creates a completely new one. That's next.